Welcome to the explainer. You know that feeling, right? When you get stuck on a derivative that just won't follow the basic rules? Well, today we're going to add two really powerful new techniques to your calculus toolkit. These are designed for exactly those tricky, complex functions that you see out in the real world. So you've probably mastered the basics, like finding the derivative of simple functions. But what happens when things get messy? When you have functions nested inside other functions, or when all the variables are tangled up together? Yeah, that's where we're headed next. Differentiating x squared? Super simple. But take a look at the function on the right. We have one function, that 3x squared plus 2, which is literally plugged inside another function, something to the fifth power. This is what we call a composite function, and it needs a special tool. And this really frames the problem perfectly. How do we find the rate of change when functions are stacked up like this? Well, it turns out there's a really elegant rule designed for exactly this situation. So let's unpack our first tool. It's called the chain rule. And this is going to be your absolute key for differentiating these composite functions. The whole function within a function problem. Okay, so the formal definition looks a little dense. I get it, but don't let it scare you. The main idea is actually really simple. You deal with the outer function first, and then you deal with the inner function. Let me show you what I mean. Here's a much more intuitive way to think about it. It's basically a two-step process. Think of it like peeling an onion. First, you handle the outermost layer, the derivative of the outside function. Then you just multiply by the derivative of the inside layer. That's it. All right, let's apply this to an actual example. We've got y equals 5x minus 8 to the fourth power. So what's the outer layer here? It's that 2 to the fourth power part, right? And the inner layer? That's the 5x minus 8 inside the parentheses. Okay, now we have our two pieces. Now let's just follow the steps from the solution. First, we handle the outer layer. That 4 comes down in front, and the exponent becomes a 3. But notice, and this is key, the inside part, the 5x minus 8, stays exactly the same for that step. Then we multiply by the derivative of what was inside, which is just 5. Do a little bit of algebra, and boom, we're done. So, the chain rule is amazing for nested functions. But what about a totally different kind of complicated? Up to now, most of our equations have been explicit, where y is all nice and neat on one side. But a lot of the time, x and y are all mixed up and tangled together, like in that implicit equation on the right. To handle these messy, tangled up equations where you can't just easily solve for y, we need our second big tool for the day, implicit differentiation. This lets us find the rate of change without having to do all the messy algebra of isolating y first. It's a game changer. Okay, this might look like a long recipe, but it's really, really logical. The most important step, the absolute key to this whole thing, is step 2. Whenever you differentiate a term that has a y in it, you just attach a dy dx to it. The rest of this is just rearranging the equation to solve for that dy dx. Let's try this on a classic problem, the equation of a circle. X squared plus y squared equals 9. Now, we could try to solve for y, but it would be kind of a mess, right? With a plus or minus square root? Yuck. Implicit differentiation lets us find the slope of the tangent line anywhere on this circle without that algebraic headache. So look at how this works. The derivative of x squared is just 2x. Easy. The derivative of y squared is 2y, but since it's a y term, we attach our dy dx. In the derivative of the constant, 9 is just 0. After that, we do a little bit of rearranging and we get our final answer. Dy dx equals negative x over y. That is an incredibly powerful formula for the slope at any point xy on that circle. So we've got these two powerful new tools. But this isn't just about solving problems in a textbook. Why should you actually care about any of this? Well, let's take a look at how these techniques are used to solve some fascinating real-world problems. As Dr. Trafer-Bozit points out, implicit differentiation is absolutely essential for solving from surprisingly tough problems within math itself. For instance, have you ever wondered how you'd find the derivative of an inverse trig function, like arctangent? So, you want to find the derivative of arctangent? Well, check this out. You can rewrite y equals arctan of x as tan y equals x. And what do we have now? It's an implicit equation. So we can differentiate both sides, use a clever little trig identity to get everything back in terms of x, and voila! We've just found a derivative that seemed totally out of reach before. But the power of these tools goes way beyond just pure math. In a field like economics, where pretty much everything is connected to everything else, implicit differentiation is an absolutely indispensable tool. Just think about a basic market model. You have this fundamental rule: supply has to equal demand. But supply depends on the price and taxes, and demand depends on the price and people's income. See how all those variables are tangled up together in one big equation? So how do you figure out what happens to the price when people's incomes go up? You got it. You use implicit differentiation. By applying implicit differentiation to that equilibrium equation, economists can make a clear prediction without even needing to know the exact numbers. In a standard market, if consumer income goes up, or if taxes go up, the equilibrium price will also go up. And that's a really powerful insight derived directly from calculus. And that's the real power here, isn't it? The chain rule and implicit differentiation aren't just some abstract rules to memorize for a test. They're like powerful lenses that let us find clear, simple relationships hidden inside these deeply complex and interconnected systems. So the only question left is, what hidden relationships will you uncover?